Welcome back. In the previous class, I have talked about the minimum time optimal problems, and we have discussed the problem formulation as well as what we have seen that for a very specific class of nonlinear system, how to obtain the optimal control which is responsible to transfer the state trajectory from the given initial condition to final some target set or final set in given or some minimum possible time. And what we found that some bang type of control comes into picture, and whatever control we have formulated bang control, their switching logic is based on the solution of a state equation and co-state equation, and also some singular interval involved whenever we are trying to solve some kind of nonlinear minimum time control problems. It is possible to show that for LTI system, linear time invariant system, that is simplest class of system, we have no singular interval. So in this particular lecture, I am going to highlight that. Most of time in this lecture, I am just going to talk about the ideas. So complete mathematical proof is missing here, and that particular complete mathematical proof is available in the papers of Pontryagin. Whenever they have defined the Pontryagin minimum principle, at that time they have given the complete proof. So main idea, just you have to understand the intuition. Okay, and if you able to understand the intuition, then you are able to design the minimum time control for linear time invariant system, or if you have some kind of nonlinear system and if you linearize your system with some kind of operating point, and if you have linear time invariant kind of system, then also you are able to apply this kind of methodology, because most of time whenever we have nonlinear system, so for some specific purpose linearization will equally work. At that time you are able to solve problem in this particular way, and due to that reason this lecture is also equally valid for those class of nonlinear problem where linearization will work fine. So let us start the minimum time control problem for LTI system. So I have very simple system x dot equal to axt plus but. Here I am assuming that ut, and here I have to become little bit specific because this representation tells us some wrong information, that I am assuming that whatever ut that basically belongs to ut that belongs to u some admissible control, and after that is subset of u, and that ut belongs to u and u is subset of Rm. And I am assuming, we have already seen that in this class of problem we are assuming in minimum time control problem that our control input is bounded by some maximum value, and here for simplicity I am assuming that that particular value is 1. So here I am assuming that 1 is also included. So I am assuming that here this is this kind of situation I have, means each and every component is bounded by less than equal to 1. Now this problem is also called linear regulator minimum time problem. So we have already deal with linear regulator problem, and here I have to define the performance measure such a way such that I am able to steer the trajectory of the system from any given point to any final point in some minimum time. Due to that reason this class of problem is known as linear regulator minimum time problem. So what we are assuming that system is completely controllable. So So what is our assumption? That my system, it means that from any initial point I can able to, after applying the control, I am able to steer the trajectory to some other point. That is the meaning of the complete controllability. And normal means I am assuming that this particular classes of problem no singular interval is exist. And later we will show by using some kind of example. No, I am not going to prove it, that particularly for LTI system, linear time invariant system, singular interval will not exist. And now I have to find a control, provided that control exists. It means that sometime control exists, sometime control not exist. So first I have to specify that particularly what class of linear system control is exist, or optimal control is exist, and which transfer the system from arbitrary initial state xt0 to final state xtf in minimum time. So that is the statement. So here I have done lot of assumption. First I am assuming that system is completely controllable. It means that from any initial condition, if I take, then by applying control I am able to transfer that system to any other point. And after that I am assuming there exists no singular point. And after that we are also assuming that if there exists optimal control which is able to transfer some system from any initial condition to final state in some kind of minimum time. And that class of problem is called linear regulator minimum time problem. So let us try to see the problem. So first of all I have to make sure that optimal control exists. So it is possible to show that if eigenvalue of this matrix, so since I have linear system, so I have axt plus but, so just you can see the eigenvalue of system matrix. So if that is non-positive real part, it means that if real part of this particular matrix is not positive, that might be negative or 0, then optimal control exists, and that transfer any initial state x0 to the origin. So this kind of proof is already given in the paper of Pontryagin. So for time being I am going to believe on this, that whatever linear system I am going to consider, for that linear system, if I do not have control, at that time also I have certain kind of stable behavior. It is possible to show that if all eigenvalue of this matrix is negative, and if that is 0, then at that time I have not a stable behavior, some kind of oscillatory behavior. So somehow I am assuming that okay, that I have some kind of not unstable behavior of the system. And at that time, if that kind of situation I have, then I can claim that there exists some kind of control or optimal control which is able to transfer system initial state x0 to the origin in some minimal time. After that, another theorem that is proved in the same paper, that is talk about the uniqueness. Uniqueness means if an extremal control exists, then that is unique. It means that whenever optimal control exists for the linear time invariant system that satisfy the necessary and sufficient condition. It means that using the Pontryagin minimum principle, if control is able to minimize the given Hamiltonian function or minimize the given Hamiltonian function, then that particular optimal control satisfy the necessary and sufficient condition. It means that only we have one control that is responsible to do that. That is the meaning. Because most of time what we have seen, whenever we have discussed the generalized Pontryagin minimum principle, at that time whatever condition we have driven, that is necessary condition, that is not sufficient condition. But for linear system, linear time invariant system, because I have I have I have talking about the extremal control, and that control will satisfy the boundary condition also. Due to that reason, I can claim that particular control will satisfy the necessary and sufficient condition for the optimality. And after that, he has also proved that if such kind of control exists, because in previous class what we have observed, that whenever we are talking about minimum time optimal control problem, at that time we have control, whatever way control is comes into picture, that will satisfy the bang bang principle. Bang bang means we have to switch between maximum limit or minimum limit, and due to that reason he has developed one theorem, and that theorem is also talks about the number of switching, that how many minimum number of switching is possible, or what maximum number of switching is possible. So that information is given by this theorem, and it is possible to show that if eigenvalue of matrix A are real, and if and unique time optimal control exists. So from the first theorem, it is obviously, I can tell that from the existence theorem, that if A is real, then obviously this kind of situation comes into picture. Time optimal control exists, and it is possible to show that each component. So suppose I have m number of control input, then each component can switch at most n minus 1 time. So that kind of result he has established. So in this particular lecture, I am going to use three theorems. First theorem talks about the existence. It means that we have to just check the system matrix. If their eigenvalue is not positive, then I can tell that there exists at least one optimal control. Second theorem is telling that if that optimal control is exist, then that is unique. It means that for one LTI system, we have just unique optimal control, which is going to minimize some given performance measure. And since we are talking about minimum time optimal problem, so performance measure, I am going to again define same like the previous class, that is nothing but T0 to Tf, and that is dt. So performance measure remains fixed in this lecture also, same performance measure. And third theorem is suggesting about the number of switching, means how many times they will take the maximum amount of control or minimum amount of control, because we have to move some quantity from one point to another point in minimum time, so I have to always maintain the extreme value. So it is possible to detect the means number of switch also, and number of switching also. So number of switching is at most n minus 1. That is the suggestion of this theorem. So let us try to see the means whatever things we have just claim using some example. I have already told you that in this particular lecture I am not going to talk about the proof of any theorems. So what I am going to do, I have taken some kind of control which is constrained by ut that is less than equal to 1. So maximum value is plus 1 and minimum value is minus 1. And now I have say very simple second order system that is represented by x1 dot equal to x2, x2 dot equal to ut. And now I have to design ut in some minimum time optimal way, such that I can able to transfer the x0 is x1 x2, so I have x0 equal to x1 0 x2 0, so I have to transfer this x1 0 x2 0 to 0 0 in some kind of minimum time. So in order to solve the minimum time problem for LTI system, we have to first concentrate on the system matrix, and you can see that from here I am able to represent system matrix like this. So from here you can see that right hand side I have, this is 0 1 and 0 0 multiplied by x1 x2. Then I can able to get r1 into c1, that is x2, and here there is no component of x1 and x2, and plus 0 into 1 into ut. And due to that reason I have written this matrix as a this matrix as a B. So under this particular convention, I have A matrix and B matrix like this. After that, now I am going to check the eigenvalue of this matrix, and you can see that here eigenvalue, both eigenvalue is 0. So how basically we are calculating eigenvalue? This determinant equal to 0. So it is possible to show that I have just this choice lambda equal to 0 0. So it means that that is not negative, that is not positive, and due to that reason optimal control exists. So from by checking eigenvalue, at least I can talk about that optimal control exists or not. And once optimal control exists, that is unique also. So uniqueness is also proof. Now we have to talk about the switching. And here you can see that I have second order system. So second order system, and how many maximum number of switching occur? So at most I have n minus 1. It means that just one switching is going to occur. So for this particular second order system. So due to that reason, this is very simple problem. Now suppose if I have third order system, then two switching will occur, 3 minus 1. So in this way, I am able to detect the number of switching for linear time invariant system. Now in order to solve the problem, I am going to use again Pontryagin minimum principle. So I have to define the Hamiltonian, and again from the coefficient of this particular performance measure, that is 1, I have substituted here, and after that I am going to define the co-state variable. Two-dimensional system, so two co-state variable is needed, and after that I have to multiply co-state variable with the right hand side of this particular quantity, so x2 and ut, and due to that reason I have this kind of Hamiltonian function. And now I have to make sure that by applying that u star, this Hamiltonian function should be minimal, and it is possible to show that if this relation will satisfy for all admissible control in this particular time interval, then I can tell that necessary condition will satisfy. And we have seen that here necessary condition is also sufficient. Due to that reason, if this condition holds, then I can tell that this is the necessary and sufficient condition for existence of the optimal control. Now let us first try to see that singular interval exists or not. What is meaning of singular interval? That try to understand for this linear system. So suppose in this particular linear system, if we are defining some kind of equation in order to find the optimal control, what we have to do? We have to define the state equation, co-state equation, by putting the optimal value of trajectory x star, optimal value of control u star, and after that optimal value of p star. So what I have to make sure that this quantity p2 star, if that equal to 0, then whatever u I will apply, that is not going to affect, and I cannot able to talk about the minimum principle. So that kind of things will comes into picture or not. So that kind of things I have to analyze. So existence of singular interval means if there exists a time interval, and this time interval, so I have final time from t0 to tf. So between this interval, I am assuming there exists such sub interval such that during that interval, whatever co-state variable, that is p2, that equal to 0. So if that equal to 0, then whatever control you can apply, that is not going to affect the Hamiltonian, because during the definition of Hamiltonian, this particular co-state variable is telling that how control is going to affect this Hamiltonian. But if p2 star, p2 or p2 star is equal to 0, then that is not going to affect the Hamiltonian. So now we have to show that p2 star 2 star equal to 0, that is not possible. That kind of things we have to show. So if we are able to show that, then I can tell that for linear time invariant, second order linear time invariant system, at least I have no singular interval. So now what I am going to do, I am going to calculate the co-state equation. So how basically we are defining co-state equation? We have to solve this kind of partial differential equation, dou h by dou h by dou x equal to, so p dot with negative sign, this equal to p dot t. So I have to solve this particular equation in order to find the optimal value. So and here all argument I have. So it is possible to show that I have these two equations, and in h, so in h I have no parameter that is related to x1 due to that region that is equal to 0, and with respect to x2 I have a negative sign here due to that region basically p1 comes into picture. So let us try to see again here. So this is a straightforward calculation. So from here, if you calculate dou h by dou x2, then p1t and with negative sign, but dou h by dou x1 that is equal to 0. Due to that reason I have two co-state equations, and if you see the solution, since this equal to 0, so that is constant, and if that is constant, then by substituting that constant I am able to see the p2 star, and if p2 star equal to 0 in some time interval, then it is necessary that c1 and c2 both equal to 0. Then only I can claim, because time is always increasing, so I have no option. So I have option like c1 equal to 0 and c2 equal to 0. Therefore what happens, that p1 star t equal to 0 and p2 star equal to 0. And one more important thing, I have to make sure that t is always positive here. Now what happens, that from the necessary condition, if from the boundary condition, or by putting p2 star and p1 star and p2 star inside the Hamiltonian, it is possible to show that is unity. But from the necessary condition, if you see the necessary condition, so necessary condition, generalized boundary condition is given like this. So inside that generalized, not necessary condition, that is generalized boundary condition. So inside generalized boundary condition, try to see that final time is free. So problem statement just is like that, in minimum time I have to transfer, but we are not talking about the specific time. Due to that reason delta tf is arbitrary. So means this quantity is arbitrary, then only in order to hold the boundary condition, whatever coefficient, that should be 0. And if you see the h is not explicitly depending on time, and due to that reason whatever performance measure I have defined, j, that is t0 to tf and dt, and here you can see that whatever h quantity, that is terminal quantity, so terminal quantity is 0. Due to that reason this quantity doesn't comes into picture. So h, x star tf, u star tf, p star tf, and t is not present, that equal to 0. But what we have seen, that from above condition, that if I substitute p1 star and p2 star, if singular interval, that should be 1. But from boundary condition is suggesting that should be not equal to 1, that should be 0. So what we conclude, that p2 star cannot be 0 during a finite time interval. It means that, and there it means that p2 star is always comes into picture, and always they are going to minimize the Hamiltonian function, and in that way we have proved that singular interval doesn't exist. So up to here what we have observed, that whatever second order, simple second order system we have taken, their eigenvalue of system matrix, that is not positive, and after that singular interval is also not exist, and number of switching, since system order is 2, that is 1. Now I have to define the control, optimal control. So optimal, in order to define the optimal control, what we have to do, we have to make sure that that Hamiltonian function will satisfy for all control. So we have to just make sure about this particular relation. So you can see that based on the coefficient of p2 star, so if p2 star is positive, then I have to apply the maximum amount. From bank principle is suggesting the same. And if P2 star is less than 0, then I have to apply maximum amount. So maximum amount of control is 1. So if P2 star is greater than 0, then I have to apply -1. If P2 star is less than, then we have to apply that -1. And due to that reason, now I have this kind of control action. From the bank principle, I have retained this kind of control action, and we have already seen that P2 star is never 0. Due to that reason, I have just two value of control. So from here I can define, and I have defined signum function, and I am assuming that P2 equal to 0 is not interesting for me. So I have defined this signum function in some specific way, that P2 star t, this is for positive. So if you take negative, then this become +1 and this become -1. In this way I have defined this control or optimal control. Now you can see that in order to find the explicit expression of U star, you have to know the P2 star t in the form of the state trajectory. So that kind of things I am going to form such that I am explicitly able to design the optimal control for this second order system. So again I am going to see the co-state equation, and we have already concluded that P2 star is not equal to 0. So basically now I have this kind of equation, P2 star equal to C1t plus C2. It means that P2, and from here it is also clear, you can see from here that P2 star can change sign at most 1. And why I am telling, because C1 and C2 is some kind of constant and t is increasing. So suppose that if initial condition is such that when this quantity minus C1t, that is negative and this is positive, then and this is more dominant over C2, or you can also think that C2 is lesser and this is C1t, and initially C2 is dominated over C1t. So as time is going to progress, then this negative quantity is going to increase. So initially if that is positive, then quantity become negative. So at most we have only one sign change, and because control action is fully depending on the P2 star. So depending on the sign change of P2 star, I have the switching of control. So due to that reason, I am just concentrated on P2 star, and based on P2 star I can claim that how many times this sign change is possible. So that kind of things I have. Now what I am going to do, I am going to, up to here, what happens that I have detected that only one time switching occur from this particular expression of P2 star. Now what I am going to do, since there can be at most one switching, the optimal control for a specified initial state must be of this form. So we have detected only one switching. So it might possible that in whole interval, so at most it means that sign might not be changed also. So in order to achieve minimum time, in order to transfer from one point to another point, I will maintain the maximum value of control. Same we have observed in the previous class when we have aircraft and we have missile and we have to pursue them. So I have to maintain maximum thrust always in order to destroy that particular missile. Or since only one switching, so either that is -1, or in some interval that is +1 and -1. So suppose that I have to move from CTA to CTB using car. So somewhere I have to accelerate very fast and somewhere I have to deaccelerate very fast. Then only I can tell that in minimum time I can able to reach that particular place, and or vice versa. And due to that reason, I have in this particular first interval might be that is negative and then that is positive. So based on the problem statement, we have just 4 different kind of situation. So in this way, by defining the number of switch, we are able to understand that what is behavior of the control. It is possible to show that I can also able to explicitly write the optimal control trajectory. So for that, now I am going to work on that particular direction. So first try to understand the segment of optimal trajectory, and in order to find the segment of optimal trajectory, what I am going to do, I am going to see the extreme value. So here you can see that in this case, if that is +1, then I have one solution. If that is -1, then I have solution, or solution might be sometime take +1 and -1. So if I know the trajectory of this and this, then I can tell that trajectory will switch between these two. And due to that reason, I'm going to interested on the extreme situation. And so what I'm going to do, I'm going to solve the state equation with respect to this. So my state equation is like this: x1 dot equal to x2 and x2 dot equal to u. So first I am going to substitute +1, and after that I will write the solution. After that I will substitute -1 and write the solution. So if you do that, then I have this kind of solution. So if I have simple equation, then I can write solution in a straightforward way. Otherwise it is not so easy task. Now what I am going to do, I am going to write the relation between solution x1 and x2 for u equal to 1. So suppose if u equal to 1, at that time I have x2 equal to t plus c3, and this is plus, again this is plus. So what you can do, you can make the square of this. So x square t, if you do, then that is nothing but t plus c3 square. So t square plus c3 into t, and after that you have some c3 4 square, something like that. And if you multiply with half, then it is possible to show that some relation like this actually comes into picture, because here I have some kind of adjustable coefficient. So I can assume that I have adjusted that coefficient in such a way, because I try to see here that I have t square plus 2t c3 plus c3 square. So c4 is nothing but c3 square, you can assume, or some mismatch you can assume. Then if mismatch, then some new constant comes into picture. Due to that reason, I have written new constant, and I have multiplied both side by half, and due to that reason half comes into picture. So everywhere I have half of this quantity. So I have relation between x1 and x2 for u when u will take maximum value, that is given like this. And once u will take minimum value, then I can easily again do the same calculation. So here that is minus, and again I will do same kind of exercise. So if you will do same kind of exercise, then either trajectory is behave like this or like this. So try to plot that trajectory. So when what we have observed, that at most I have one switching. So suppose if system, this particular system x1 dot equal to x2 and x2 dot equal to u, and if that will take u equal to +1, at that time I have trajectory that is x1, that is half x2 square plus some quantity like c5. So if c5 greater than 0, then I have parabola, that is shifted parabola from origin. If c5 equal to 0, then I have some kind of exact parabola. So and I hope that you all are able to understand that whenever I have this kind of equation, then that represents some kind of parabola. So I have certain kind of parabolic trajectory. Similarly, now if I have u minus 1, then just since equation is x1 dot equal to minus half x2 square and plus some c6, so here just parabola remains the same, but their orientation become opposite, and due to that reason now I have parabola like this. Again c6 that greater than 0, then parabola pass through here, and if c6 less than 0, then parabola pass through here. So this is the extreme situation, and I have already told you that in some situation it might possible that trajectory might be pass, sometime they will take maximum value, sometime they will take minimum value. So sometime they will consider take u star, and sometime they will take u star equal to +1. So for that, now I have to define some kind of switching curve. And how to define that switching curve? By putting constant equal to 0, because finally I have to converge to this equilibrium point 0. Due to that reason, just I have to select those curve which is passing through the equilibrium point. So here one curve, this curve is passing through origin, and after that this curve is passing through origin. So if I will switch along this curve, then it is possible to show that I can achieve the equilibrium point. Due to that reason, I have shown this two trajectory only. So from the several initial state, because initial state switching is basically driven by P2 star, we have just seen. So now what we can see that this particular curve, and I have represented the curve how basically we have, because for x2, when x2 is positive, at that time I have half x2 square. If x2 is negative, at that time I have some other quantity. So this is not like this. Only one place I have absolute value. One place will able to give the sign. So if x2 is greater than 0, at that time I have equation like half x2 square. If x2 is less than 0, at that time I have equation like half. So this will give the magnitude as well as this sign, and this will always give the magnitude. So in this way I have defined this particular switching surface. And after that, now it is possible to show that if trajectory, sometime trajectory is positive, then somewhere that will hit the surface, and after that they will maintain. So I can express the optimal control like this. So I will define the surface, and this surface is nothing but switching surface. This is the switching surface. So by solving the optimal condition or extremal condition, I am able to define the switching function. And once definition of switching function is fixed, then it is possible to show that for second order system, switching function is divide whole plane in two part. So if xt greater than 0, then what happens, xt lie above the switching curve AOB. So same kind of things I have written here, that if that is greater than 0, then that is above the AOB curve, means in this particular region. So if that is greater than 0, then I have to apply -1. If that is in this region, then I have to apply +1. So same kind of things basically we have written here, that if xt less than 0, this implies xt lie below the switching curve, and if xt equal to 0, so I have just three regions now, either xt greater than 0, less than 0, or equal to 0. And why we can conclude, because this is one dimensional quantity. You can see that whatever switching surface I have defined, that is one dimensional quantity. So just we have three different possibilities, either that is greater than 0, less than 0, or equal to 0. But if you have two dimension, then I have several different possibility. I cannot tell some quantity just greater than 0, less than 0. I have several different possibilities. So what we have done, using the proper switching function, first I have transferred my two-dimensional problem into one-dimensional problem, and after that now I have this kind of logic. And in this way, now explicitly I can now able to define the optimal control. So that equal to -1 for xt, such that if xt is greater than 0, less than 0, then what I am going to apply, I have to converge toward xt equal to 0, because finally I have to converge to the 0 only. So due to that reason, I will select +1. And if xt that is equal to 0, but x2 is greater than 0, then I have to apply -1. And similarly, when xt equal to 0 and x2 less than 0, then I have to apply +1. So from this particular curve, analysis of particular curve, I am able to define the explicit nature of the control. So my optimal control is now this particular. So explicit expression of optimal control. Why I am telling explicit expression? Because now everything in terms of the state, that is not in terms of the co-state variable, and state is known. I am assuming that both states information are available to me, and using that information I can able to design this kind of bang control. Now let us try to see that if I have some Again I have second order system, and at this time I am going to modify the system matrix, and I have added this particular mode dynamics minus AX2 inside the system dynamics. And again now our aim to, I have some arbitrary initial condition x0, and I have to transfer to the origin in minimum time, and again control that is constrained by this number, and a I am assuming that is some kind of positive quantity, so a is actually here. And after that, now what I am going to do, first I am going to check that optimal control exists or not. And what we have seen that for existence of optimal control, just we have to make sure that eigenvalue of system matrix that is not positive. So either 0 or negative, that is fine, and in this particular matrix whatever problem I have considered that will satisfy, it means that optimal control exists. And if optimal control exists, that is unique, so uniqueness is proof. And I have second order system, so at most one switching is only comes into picture. So whenever we have some kind of second order system or third order system or fourth order system, LTI system, and we have to define the optimal control. So first step what you can do, you can select the extremal value of the control, so either maximum or minimum. So and based on that, what you can do, you can find the set. So what I am going to do, I am going to define two set, O plus and O minus, from which one can reach by applying u plus and u minus 1. And so for some specific initial condition, if I apply this kind of control, then directly I am able to reach to the equilibrium point. And because I have only at most one switching, so in some initial condition it is possible that if I will just apply u plus 1, then I can reach to the equilibrium point. If I apply u minus 1, then again I will reach to the equilibrium point for some other initial condition. But in large class of initial condition, I have to switch between two control, u plus and u minus. So if you are able to select the extreme one, and if you take the union and create some switching manifold, then you are able to define the bang bang control. So same kind of logic I am going to apply here. So first what I am going to do, I am going to solve the differential equation by taking the extreme value, that is plus minus 1. And here solution is also not difficult. Why? Because here I have some kind of linear equation, first order linear equation. If you just see this particular equation, so I have x2 dot t minus ax2 plus 1. So either you can apply variable separation method, or if you know the solution of ax plus bu t, so using that solution also I can able to find this. So those who are not aware about this solution, so for that I have already recorded lecture that how to solve the linear time invariant and linear time varying system in modern control theory course. So EE-313 course is available on YouTube. From there you are able to see that how to solve this. So I have solution of this, and after that putting that solution I can also able to write the second solution. So I am assuming that okay, these two solution is available to me, and once I have solution, then now you can see that if x1 and x2 equal to 0 at t equal to 0, then I can conclude that c1 equal to 0 and c2 equal to 0. It means that I have to pass those kind of trajectory in extremal way that pass through the origin, because my goal is to transfer from any arbitrary condition to origin. So that is our goal, and due to that reason I have find both trajectory, both extremal trajectory. And now what I am going to do, I am going to define this set O plus by selecting u equal to plus 1, and in this way I am able to find the relation between x1 and x2. Similarly, at this moment what we have observed that x2 is less than 0. So from here, if you see this particular expression, in this particular expression about x2, because this is explicit in terms of t, so from this expression I can able to comment about the sign of x2. So if x2 is greater than 0, less than 0, then I have this kind of expression. And if x2 is greater than 0, then and u equal to -1, it is possible to so I have this kind of equation, and by combining these two I am able to define the switching manifold. So this is my switching manifold, x1t equal to this. So at switching manifold I have this. So in order to define switching manifold, what I am going to do, I am going to take the x1 minus of this whole quantity, and in this way I can able to define the switching manifold. So you can see that switching manifold is defined like this. So here a is some kind of constant quantity. So if you change a, then I have different kind of curve. Obviously this is not parabola. Why this is not parabola? Because I have some kind of logarithmic function here. So by different a1 I have different curve. And suppose that for some particular example, if I select a equal to half, then I have this kind of curve. And again, now what happens, that if trajectory is going to lie in this particular place, because at most one switching is allowed, due to that reason they will converge to here. If that will lie here, then that will converge to here. If they will lie somewhere, then they have to switch between two things, and after that, in this way I am able to comment about the time optimal control. So I have switching manifold, I know the switching manifold. So based on the switching manifold, now what I am going to do, same way, that when xt that is greater than 0, then I have to put signum equal to -1. If xt less than 0, then I will put that equal to +1. Similar way, whatever way we have defined. And after that, if xt equal to 0, then at that time xt is exactly means equal to 0, at that time my control equal to 0. So same way I am able to define the control. So that part actually I have just left for your exercise. So in this way, at least for second order system, I am able to define the bang control or time optimal control. Obviously this construction one can do for third order, but you can see that control become very complex for third order. So even if I can theoretically I can tell that some kind of time optimal control exists, but in order to implement that particular control, first I have to define the switching manifold, and after that we have to define the control in proper way. So that is not so straightforward job. So due to that reason, most of time whenever I have system that is lower order, then only we are talking about time optimal control design. So with this remark, I am going to end the today's lecture. So before ending, what we have observed, that for linear time invariant system, I have very clear cut way to make sure that optimal control exists or not. So just I have to see the system matrix, and if system matrix a eigenvalue of the system matrix that is not positive, then I can claim that optimal control exists. And once that will exist, that is also unique, and after that we are also able to define the number of switch, how many times they will switch, and using the formulation of Hamiltonian, we are able to define explicit nature of optimal control. Why? Because in this particular classes of system, singular interval will not exist. So I haven't give the concrete proof. Several proof I have skipped in order to make the discussion concise. But if you have interest, then you can further or after the completion of this course, you can go through the paper of Pontryagin, and after that try to understand the proof. Proof is also not too much difficult. So with this remark, I am going to end the today's lecture. So thank you very much.